Good day to you. I am Manisha GDas. I am an architect and I'll be representing what we do at ARK, Architecture and Research Kinetics, in the space of BIM implementation and automation from India. Allow me to tell you how ants find the shortest path to the food. It's called pheromones. Ants release a chemical called pheromones, and as they move, the more ants follow a path, the stronger the pheromone trail becomes. This helps other ants define an efficient route. Inspired by this, ant colony optimization or ACO is a powerful algorithm which is used in design and engineering. It simulates how ants search for food to solve complex problems like finding optimal routes in network design or even coding. How robots move by mimicking ant behavior. ACO can help designers and engineers discover the best solutions faster, saving time and resources in the design process. The traveling salesman problem, or TSP, asks a very simple question. Given a list of cities, what is the shortest route that visits each of these cities once and then returns to the starting point? But here's the catch. The problem is an NP-hard problem. That means the number of possible routes grow exponentially, making it exceedingly difficult to solve as soon as the number of cities goes up. Specifically for n cities, there is an n-1 factorial by 2 possible routes to consider. So for just say 10 cities, it is about 180,000 routes. So why does TSP matter in design? It's crucial for optimizing logistics like delivery, routes, or even in designing circuits, designing pathways, networks to minimize cost and time. Mapping and solving a TSP can efficiently lead to a smarter design, saving both resources and efforts, and can be applicable to nearly everything from urban planning to manufacturing to design to operations. In design, it is all about finding the most efficient path, and that is why TSP becomes so relevant to the field of design and construction. So allow me to introduce ARK. ARK is a small design firm started back in 2004, and we are now largely into BIM implementation, automation, AI, and ML. Why is it so essential that we feel that AI and ML and BIM implementation has to be brought into the design process? Well, the reason being that this eliminates errors. It helps data-driven design decision making for all stakeholders. And the manner of doing it, which is BIM implementation or integrated design and delivery, is not something which is very common to our industry, especially in India, UK, US, wherever we have worked. As change agents and digital transformation agents, we are able to help a lot of the teams bring or leverage the power of AI for the designs. BIM, as we know, is a very fragmented and has many dimensions and disciplines within that for design. We are dealing with MEP engineers, environmental consultants, contractors, subcontractors, interior designers, architects, structural engineers, and each of us require a very different set of information. The cost consultant will never need the same information as maybe what the landscape engineer or the landscape designer requires. And having this one true source of information, which is the common data environment, and managing it correctly, plus leveraging it for with the use of automation, with the use of data mining, it ensures that the relevant stakeholders get the correct information at the correct time without expending too much of time and effort behind learning new applications, investing behind new applications and software, etc. BIM is essentially a systematic process. The BIM iceberg model, introduced by Finit Jenningen, represents how BIM maturity and systematic thinking can require a well-managed effort for implementation. An architect studio, that's where the entire process starts, of the stack of graphical and non-graphical data. It has to be correctly handled, and the organization has to begin at the studio. for any further analysis, design, construction, scheduling, cost crunching, asset management, and finally to the handover and the operations. ARK leverages automation for repetitive tasks like data validation, clash detection, and code compliance, freeing up time from the resources and for many strategic design considerations, especially. Additionally, meta-heuristic algorithms like genetic algorithm and colony optimization are employed to optimize design solutions, sequencing, optimizing layouts, routes, etc. Meta-heuristic algorithms are high-level problem-solving strategies used to find near-optimal solutions for complex optimization problems, particularly when exact methods are too slow or impractical. Now, they work iteratively, exploring the search space using techniques like randomness, local search, and guided exploration. Examples, of course, include genetic algorithm, which is used by refinery, simulated annealing, and ACO, particle swarm, etc. So the question arises: where does ACO or metaheuristic algorithms, where do they come in into our designs? So we often use these for optimization, as we earlier said, for tasks like clustering, organizing spaces in architecture, civil engineering design, building services design, etc. And the reason being that ACO plus BIM or meta-heuristic algorithm plus BIM is an explainable low computational expense solution and quick and good enough solutions to otherwise lengthy manual error-prone iterative exercises. So instead of a black box machine learning or an AI solution, which would depend upon a neural network or CNN, we look towards optimization algorithms and meta heuristics. Also, if the problem at hand is easier to map to any of these meta heuristic algorithms, like say using TSP or knapsack problem, etc. So, for example, we mapped a room numbering and sequencing problem to traveling salesman problem with the use of features or parameters like volume, size, number of connections, doors, departments, Euclidean distance, and even using the status of front of house or back of house for the particular room. Now, this lent us a set of parameters with a choice of weights, which we then mapped to a cost function. The cost function eventually was put into an ACO, and then a certain number of runs or algorithm runs were done to find out what would be the most optimal set of weights. Finally, the weights were taken to an ANN or an artificial neural network to figure out how they can be tuned to effectively give us the best solution. These are the runs. So this was the first one with a certain set of parameters. The next was the iterations that were done with various changes. This was another iteration which was quite chaotic, as you can see. And this was a sort of a record which was done for the model runs and how many minutes of computing time or computer time that it really took, the GPU time. Finally, if you look at this particular iteration, this was the most ideal or the shortest route that came up. In this, of course, this was trying to near the Euclidean distance baseline which we had created. And you can see most of the weights were considered as 0 for the parameters. But later, this exercise went to ANN and there were better solutions that were achieved. This was how it was mapped to the actual plan. And then the live project output was considered for this room numbering. This exercise was done iteratively throughout the design process. The final conclusion, or what we say the successful takeaways, would be that yes, it could correctly identify the sequence, it could map the particular rooms correctly. Where all we can improve, of course, that ACO is only as successful as the simplest Euclidean distance problem for now without the ANN fine-tuning of the parameters. And also that we would be looking at next steps where we are taking it to different kind of solutions. We are looking at different algorithms as well, the particle swarm, genetic algorithm, etc. So other than meta-heuristic algorithms, we're also exploring lots of linear programming, transportation, assignment problems. Furthermore, we're looking at networking algorithms, random forests, etc., etc. In this particular exercise, we were looking at allocation of spaces using a very simple assignment problem to the correct zone in a particular given exercise. So we're experimenting with how simple algorithms can also be utilized for design exercises. This was one of such exercise. And then data, you can see that it was, so this was the application of the assignment problem solution to the floor plan. And that's a thank you. Thank you for your patience, and I would love to hear more from you. Goodbye.